Hey guys, and welcome to your third online web lesson. This lesson has to do with proving triangles congruent. Okay, and this is from lesson 5-4 from your book, so if you want to peek in there, if you didn't happen to understand the way I explained something, you can always look at your book, which is a great resource. And it also has worked out examples of the problems that you have to do. So never be afraid of looking at your book for a little bit of help. So let's talk a little bit about triangles. Okay, you'll remember from the last lesson where we said that what it means for two triangles to be congruent, and ignore the fact that this one is a bit bigger than the other. What it means for two triangles to be congruent is that all of the corresponding parts are also congruent. So that means that AB is congruent to DE, BC is congruent to EF, CA is congruent to FD, and angle CAB is congruent to angle FDE, and so on. And there we have two lovely congruent triangles. And if I were going to write a congruent statement, it would just be something like this, so that all of the vertices match the others, and D, E, F. Yay! Great. Okay, so far so good. That's something that's review for us, and hopefully that should be pretty clear by now. Now here's a question, and it might scare you because it has to deal with proving, and yeah, we're going to do a few formal proofs. The question is, how could I go about proving, and I'll put this sideways, how could I go about proving that these two triangles are congruent? Well, we know what the definition of congruent is. So really the simplest way, and I'll give these vertices names, T, U, V. The simplest way would be simply to go about and showing that each part is congruent to every other part of the other triangle. And that might take us a little while, but we could do it. We'd just have to we could measure QR and measure TU and show that they're congruent. Then we could measure RS, measure UV, and show that they're congruent, and so on with the angles as well. And once we proved that each of the 6 parts of the triangles are congruent, we could show that the two triangles are totally congruent. So that is one way. But of course, that's a little bit annoying to do, right? It's a bit of a hassle to go through 6 steps to prove that the triangles are congruent. Now you remember we said that what's interesting about triangles in geometry is that they have all these special relationships, so that if you change one part of the triangle, you're going to be changing other parts of the triangle no matter what. I can't change this angle without changing other parts. For example, side RS is going to be different. And so maybe I don't have to actually show that every part of the two triangles are congruent. Maybe I can only show that some parts are congruent, and then the rest will logically also be congruent, and I won't have to prove it. Well, let's see if that's possible. Let's think about these two triangles. I'll undo this little rotation here. U, V. Let's think about it. What if I proved that side QR and side TU are congruent? The question is that enough to show that all the rest of the parts are congruent? As in, could it be possible for QR and TU to be congruent and other parts not be congruent? Think about it. Well, a possible counterexample would be, well, what if this side was a bit longer than this side? Could QR and TU still be the same length? Yeah. So it doesn't seem like proving that two sides are equal in length is going to be enough. Well, let's think about doing two sides. Okay. Is it possible that these two sides could be congruent and other parts of the triangles would not be congruent? Let's think about it. Can you think of a possible counterexample? Well, let me try to modify something. What if I kept QR, what did I erase here? S. What if I kept QR and RS congruent? I didn't change the length, but I changed the length, the measurement of this angle. What if I made it a bit smaller? Can I still have QR and RS congruent to it? Can I have this congruent to this and still RS congruent to UV? And have a different length, a different measurement of an angle at the top? Yeah, it seems like that's possible. There's nothing logically wrong with that. So it doesn't seem like proving that two sides are congruent to each other, two pairs of sides, is enough either. Okay, so what about three sides? Is this going to be enough? Well, let's think about this. Is it possible for all the pairs of sides to be congruent and have angles that are not congruent to each other? Let me think about that. That's tricky. Well, let's say that this side starts out being congruent to this. Yeah. Now, what if I wanted to change one of those angles so that they're not congruent anymore? Let me see, for example, what if I made this angle a bit bigger than this one? There you go. Ha! I beat it. They're not congruent anymore, right? That's true, they're not congruent. But if you see, in order to do that, I had to make this side longer. And I also had to make that side longer. Right? So in the process, I actually lost the fact that these two were congruent. Right? So this is not going to be a counterexample. And if we work it out, it actually is going to be that there is no way of having all the sides congruent between the triangles without having also congruent angles. Another way to think about that is, imagine that I flattened out this triangle. If I broke it apart, if I took some scissors and I cut it right at the top, and I just spread it out, let's see, spread it out something like this. Right? Here are my sides. And then what if I cut this one too, right? Remember, the sides of this are equal to the other sides. So let's say that it's going to be like that. And if I did the same here, it would be something like that. Now the question is, if I were to fold this into a triangle, right? If I were to take each little piece and kind of swivel these around, swivel them like that into a triangle, and swivel these around into a triangle, is there any way that I could swivel them so that the angles would end up being different? Right? There's actually no way. No matter what I do when I swivel them, they're going to stop at the exact same place, leaving me with the exact measurement of angles at each vertex. So it turns out that in order to prove two triangles are congruent, I don't actually need to prove that every single part, every single side, and every single angle are congruent. It's actually enough just to prove that three sides are congruent. And along with those sides, I get the angles, right? Because there's no way of changing the length without changing the angles. So this is called side-side-side congruence, or often you'll see it's called SSS. And it's basically, we could call it the SSS postulate. And that's just one of those fancy math terms that means that this is true in every case, no matter what the triangles are. If all of the sides are congruent, then the entire triangle is congruent. Right? So if I were going to do a geometric proof using this SSS or side, side, side postulate, all I would have to do is prove that the three sides are congruent. So let's try just a quick example of a proof that uses this SSS postulate. So I'm gonna do a diagram. Okay, and that's supposed to be y. There you go. And here I have a triangle BYA, and I have a triangle CYA, and my given is that segment AB is congruent to segment AC, and use a little semicolon, segment BY is congruent to segment CY. Right, BY, CY. And I'm just going to go ahead and put those on the diagram because that'll make my life a bit easier. And AB congruent to AC. Whoa. There we go. Okay. Now, what do I have to prove? Let's see. Prove that triangle BYA is congruent to triangle CYA. Okay, so let's try to figure that out. Here we have the statements, and here we have the reasons, and it's going to be a short proof, so I don't think I need much more room than that. Okay, where do I start? Now, you might already guess that I'm not going to have to prove that every little part is congruent to every other little part. In fact, this is a lesson about SSS, and so the chances are we're going to have to use SSS to prove that these two triangles are congruent to each other. Okay, so let's start out. As you know, we always start with the given, so that's pretty quick. We go from AB is congruent to AC, and BY is congruent to CY. And that reason is, of course, given. I know that because the book told me. Okay? Now, where would I want to go in order to prove SSS on these two triangles, in order to prove that the three sides are congruent? Let's take a look. I already see that I have two pairs of sides congruent. Now, what's the missing side? It's this one in the middle, right? So if I can prove somehow that side AY, this part of this triangle, is congruent to this part of this triangle, then I'm going to be able to prove that the two triangles are totally congruent, that all the angles and all of the sides are congruent to one another. Now, how could I go about proving that? Well, it might seem a bit silly because this is actually the same line segment, right? So of course it's going to be congruent to itself. It can't be different from itself. So if you think back to the last lesson, you remember that we had a property that says that all quantities are actually equal to themselves. And in the same way, all segments are congruent also to themselves. So can I say that AY, segment AY, is congruent to segment AY? Well, yeah, of course. And that, if you remember, is called the reflexive property. Think about it as the reflection, right? It's the reflection of itself, and of course equal to itself. So I can put that right here. And so do these two triangles have three sides that are equal in length? Yeah, so I'm pretty much done. I know, based on, I'll just say the reason first, side, side, side postulate, I'll just put SSS, that triangle BYA is congruent to triangle CYA. And so that is an example of a very, very short proof of how I can use this to prove that the two triangles are congruent. Now, is this true? Yeah, because we already proved that the entire triangles are congruent, so of course the angles are congruent. So this is also true, and this is also true. Right? And that's an example of a quick way of showing that two triangles are congruent without having to show that all 6 parts are congruent. Okay? So we'll just leave it at that. The chapter actually has a little piece on SSS, which is side angle side, which we'll look at next lesson. So what I'd like you to do as an assignment is, and I'll post this also on the blog, I'd like you to do check for understanding, number 2, number 5, no, not 5. Yes, I want you to do number 5, which is going to be a proof. Very simple proof. And I want you to do 7 and 8. Okay? So do your best and bring it into class, and then we'll talk about it and go from there. All right. See you guys. Bye-bye.